Hello and welcome to another Stephen Mendes video. This video is not for beginners. It requires some knowledge of maths. It requires some knowledge of electronics. It's specifically for final year students doing control systems theory modeling. So here we have a simple circuit, serial RLC circuit. And we are going to analyze this circuit so as to find its transfer function. And we're going to do this by first finding the signal flow graph and then using Mason's gain formula to get the transfer function directly from the graph. And then we're going to also use the alternative method of putting the equations into a state variable model. Okay, so both of these things will lead to the same results. And as I said, you will see for yourself what's involved as we go along. Right now, we've just written the defining equations for a capacitor and a coil inductor that relate the voltage to the current flowing through them. We use Kirchhoff's law around the loop, going in the clockwise direction, and using those equations, we can get everything in terms of the current in the circuit except for V, the initial voltage. We rearrange these equations to have the differential first order derivative on the left-hand side as the subject of the equation as shown. Now when we do this, this gets it ready for the state variable model because the model itself is based on equations that bring about a change, and the change is caused by this first derivative, which can also be denoted with a dot above the variable. So we have two variables in this case, I and Vc. And as you can see, if we make I x1 and Vc x2, then x1 prime will be the first derivative and x2 prime will be the first derivative of the other variable that we're trying to put into the model. Okay, so there the equations have been rearranged, substituting for x1 for I and x2 for Vc. And we can put those two equations now into the state variable form, and we can also draw the signal flow graph directly from the two equations. All right, on the right hand side you see that is the standard form of the state variable model, where A, B, and C are matrices, and X and X prime a vector of values of the various variables. In this case, we only have two, x1 and x2. Now, as you can see, we are populating the matrix, and it comes directly from the equations above. But first we're going to explain the signal flow graph and how we get that signal flow graph from the two equations above. We're going to go back there and follow that slowly. First of all, we move from V, and we see that V is multiplied by 1 over L, which is a gain. Then we see that when we get to the other point, it's a summing point, and we are summing not only 1 over L times V, but we're also summing minus 1 over L x2 and minus R over L x1. So this is manifested in those two feedback loops, where x2 is feeding back to the add point through a branch labeled minus 1 over L, and x1 is feeding back to the add point through the branch marked minus R over L. So in fact, the branches represent the gains or multipliers or coefficients, if you will, of the various variables and terms in the expression. And it so happens that because of the way we have defined it, if you look back at the diagram, the output is x2. So that's the reason why x2 is on the rightmost side of your signal flow graph, and the input is V, or the voltage source. So it makes perfect sense. And where we have the 1 over S marked on an arc, from the Laplace transform, you know that 1 over S is an integration. So we're integrating what is at the add point to get x1. And that exactly happens. If we integrate x1 prime, we do end up with actually x1. And the same is true to get to x2. We get to x2 from x2 prime. Notice the path. The path comes 1 over C, which is the gain, and it's coming from the x1 node. So it goes through the 1 over C, which is the multiplication of it. Then it reaches a point there, and then it goes through an integration to move from x2 prime to x2. So that where the arrow points to is now x2. So you should be able to draw both the nodes and the arcs for any set of equations. It's important that you know how to draw a signal flow graph for a set of equations. And we've already showed you, or we're going to show you now, how to put the equations into the matrix A and B. We've labeled the columns of the A matrix x1 and x2, and of the C matrix x1 and x2. So basically, the top row marked equation 1 in light blue shows that we have minus RL times x1 added to minus L times x2, and also added to 1 over L V. The U on the right side of the state variable model just means the initial conditions, and our initial condition is the voltage V. So that's why I've put a V over the 1 over L. Now when we come down to the second row in brown, which is the second equation, we see that we have no v in there, we have no x2, which is why you see the zeros, and we only have 1 over c in the x1 column. The x itself would be a vector containing both x1 and x2, and the x prime would be a vector containing x1 prime and x2 prime. Now we see in the case of the output y that the x vector, which contains x1 and x2, is multiplied by the c vector, and since the 1 is in the x2 position, it's 1 times x2, which is exactly what y is. Y is just x2, and there's no x1 in y at all, which is why there's a 0 there. So I'm sure that if you study this, you will be able to figure it out. So let us move on. Right. We're going to continue to work with the state variable model, which we defined in the last situation. And we're just putting back the stuff that we had before. Now, Mason's gain formula is what we're going to look at. How to use Mason's gain formula on this graph now to be able to find the transfer function. Step 1 is just to multiply the forward path gains. There's only one forward path going from v to x2. So we take all those terms along the way from v to x2 and simply multiply them together as shown. So our forward path gain in the forward direction from v to x2 is merely 1 over L, 1 over S, 1 over C, 1 over S, which comes out to 1 over LC S squared. Now, we need to take the A matrix and do some stuff on it. But first, we show you how to find S times the identity matrix. We multiply S by the identity matrix, and the result is with S in the diagonal as shown. We now proceed to take a look at how we're going to continue in both of these operations. To make the video a little shorter, I'm going to go ahead and skip some of the things. So I've put it at all in one here because we're trying to get through. We're up to 15 minutes in the video. But I've identified the loop gains there in the signal flow graph. There are two individual loops involving backwards as well as forwards. In the first loop, you only have two things. You have minus R over L and 1 over S. And in the larger loop, you have minus 1 over L, and then you have three forward things, 1 over S, 1 over C, and 1 over S, as ticked there in green. So for the second loop, you have minus 1 over L, C, and S squared. That should be obvious as you study the loop. So those are the two loops there. Now, going to the other problem that we're working on, we now want to subtract the A matrix from our matrix that we developed on the last slide. So we have that matrix there to do a subtraction. And if you subtract each element from each other element in the S matrix times the identity matrix, you will come up with what we have got there. So you can take your time and do that. All right, proceeding now further on with both of them. We have a very simple case of a signal flow graph here, and there are no non-touching loops. All those two loops are touching each other, which means they are using common segments or branches. If we had a non-touching loop, it would be completely isolated from the other loops. So if we have no non-touching loops, that simplifies everything, and we don't have to teach you about loops that are non-touching, doing more complicated signal flow graphs at this point in time. So all we have to do now is to skip the other step and then find the final determinant of the graph. Now over on the side where we're dealing with our state variable model, what we really want there is shown. We now want to find the inverse reciprocal matrix of what we have found on the previous slide. So we're going to do that now. Now the process of finding an inverse matrix is shown there for a square 2 by 2 matrix is shown there in yellow on the left hand side. And we proceed to apply that to the one that we have there in green at the top. We swap the A and D elements, we negate the B and C elements, and we find the determinant, which is shown as a quadratic equation in S on the right hand side. Now proceeding further, we're going to divide each element by the determinant as shown here. After we've done that, after we've divided each element by the determinant, we have to multiply our C and B, in this case vectors, by our matrix. Now if you're not familiar with matrix math, you might not know how to do this, so we're going to go through it, and it's shown here fairly clearly. We take the vector on the right and we multiply it so that the column where the 0 is in the vector, that makes both of our columns of our matrix become 0, and the 1 over L multiplies the other two. But because now we have to multiply that matrix into the vector on the left, and we have a 0 element there, it turns out that when we multiply all of those things together, the only element of the A matrix that's actually used in this case is the one on the bottom left, which I've circled in blue. I have then expanded the multiplication there where we have 1 over L multiplied times 1 over C times the determinant. And as you can see, after a little algebra, we have the final transfer function shown here in blue. Now we go back to our signal flow graph, and we're now looking at the purple on the right hand side to find the determinant of the graph itself, it is 1 minus the sum of the individual loop gains. We don't have to have any more in that expression because we have no non-touching loops. So we take our 2 loop gains and we put them in there and multiply them together. Add them together. And inside the brackets, that is. And that goes at the bottom, whereas the forward path goes on the top. And there we have our transfer function. All we have to do now is to multiply it by s squared, and it comes out to the same answer as we got from using the state variable matrix. Thanks for watching. It's been a long video. If you need to go back and figure it out, that would be appreciated so that you may get top marks in this type of work. See you in the next video.